All right, let's dive right into this. Welcome to our explainer. Today, we're exploring a seriously fascinating and completely invisible battle of physical chemistry. We're talking about how scientists literally force unmixable things to mix. Think about the powdery ingredients in your cough syrup, or the oil and water in your favorite hand lotion. Getting those to stay perfectly mixed on your bathroom shelf against all odds, well, it's basically a microscopic war against the laws of nature. Here's our visual roadmap for today's explainer. We'll kick things off with the coarse dispersion dilemma, then look at how suspensions fight gravity and how to actually formulate perfect ones. After that, we'll shift gears into emulsions, mixing the unmixable, how to prevent them from breaking down, and finally, we'll wrap up with the HLB system. So, Section 1, the coarse dispersion dilemma. Now, the absolute crucial point here is this. When you grind a solid down into tiny particles to float in a liquid, you're massively increasing the total surface area of that solid. And in physics, high surface area means high surface free energy. These tiny particles become highly energetic, and, well, nature absolutely hates high energy states. They desperately want to regroup and clump back together just to decrease their total area. What this really means is that every coarse dispersion is fundamentally thermodynamically unstable. We are quite literally fighting the laws of physics here. Let's see how this sets the stage for our first combatant, suspensions. A suspension is, at its core, a solid in liquid mixture. Think of that liquid oral antibiotic you always have to shake up before taking. The goal sounds simple enough, but it's incredibly tough to pull off. Those solid particles shouldn't settle too rapidly, and if they do settle, they absolutely must not form a hard, unbreakable cake at the bottom of the bottle. Moving on to Section 2, suspensions, fighting gravity. When we're fighting to keep these solid particles floating, gravity is our main enemy. And based on the mathematics of Stokes' law, we actually have a few tactical options to slow down that settling. First up, particle size. Because size is squared in the equation, if we grind particles down to half their size, the settling rate doesn't just cut in half, it drops by a massive factor of 4. We can also thicken the liquid, increase the viscosity to slow things down, though you gotta be careful there so the medicine can actually still pour out. Or we can try matching densities. If the liquid and the solid have the exact same density, which scientists often achieve by adding stuff like glycerin or sorbitol, the settling just stops entirely. Pretty neat, right? Now, what's really fascinating here is this highly specific distance. When particles in a liquid are separated by exactly 10 to 20 nanometers, they enter the state called a secondary minimum. At this very precise distance, weak attractive forces start to take over. And scientists actually use this quirk of physics to their advantage. They encourage the particles to purposefully form these loose, fluffy clumps called flocks. But wait, why would we actually want clumps? Well, let's compare our options. If we prevent all clumping and keep the particles totally separate, we get what's called a deflocculated system. Sure, they settle slowly, but when they finally hit the bottom, they lock together into a hard, concrete-like sediment that you literally cannot shake back up. It's ruined. But if we encourage those fluffy clumps we just talked about, creating a flocculated system, it does settle faster, but the sediment forms a loosely packed network. It's kind of like a fluffy snowbank. Just a quick shake of the bottle and it easily redisperses perfectly. Since that fluffy snowbank is the ultimate goal, pharmacists measure their success using a specific mathematical parameter. It's called the degree of flocculation, or beta. It's pretty straightforward. It just compares the final volume of our fluffy, flocculated sediment to the volume of a completely hard, deflocculated sediment. A higher beta value? That proves we've successfully created that fluffy, easily dispersed network instead of a useless, hard block of medicine. That brings us to Section 3, formulating perfect suspensions. So knowing all of this, how does scientists actually build a perfect, shelf-stable liquid medicine from dry, water-repelling powders? They follow a pretty brilliant 3-step strategy. First, they have to overcome the powder's hydrophobic nature by coating it with a wetting agent, which lowers its contact angle so it actually accepts the water. Second, they add electrolytes or polymers to intentionally induce those fluffy flocks we just covered. And finally, step 3, they trap those flocks in a structured vehicle. This is basically a hydrocolloid gel that holds the particles completely still while sitting on the shelf, but, and here's the magic, it instantly thins out into a liquid the second you shake it. Okay, so we've mastered keeping solids suspended in liquids, but that leads us to an even tougher question. What happens when both phases are liquid? How do we battle thermodynamics when we're trying to mix two completely immiscible, or unmixable, liquids together? Think oil and water. Which brings us to the second half of our explainer, Section 4, emulsions, mixing the unmixable.
Whether we're talking about a flowing oral medication or a thick, luxurious skin cream, an emulsion is basically taking oil and water and forcing one to disperse as tiny droplets into the other. And just like with our solid powders, these tiny droplets create an enormous surface area of high free energy. The droplets want to rapidly fuse back together and separate into two distinct layers. They really want to. Unless, that is, we build a kind of chemical armor around the droplets using an emulsifying agent.
To build this microscopic armor, scientists deploy three main types of mediators. First, we have synthetic surface-active agents, like spans and tweens, that lower surface tension and create a slick single-molecule layer around the drop. Then we have natural hydrophilic colloids, like acacia gum or gelatin, which build thick, physical, multi-layer walls. And finally, believe it or not, we can actually use finely divided solid particles, like bentonite clay, which swarm the droplets to act as literal physical barricades, preventing the oil and water from ever touching. All right, Section 5. Preventing emulsion breakdowns. Now, despite all this impressive molecular armor, these liquid systems are constantly under stress from gravity and temperature. There are essentially four ways an emulsion can break down. If you look at reversibility, it's pretty revealing. While creaming, where droplets just float to the top, and flocculation, where they gently cluster, are reversible separations you can easily fix with a good shake, the other two are absolutely catastrophic. Coalescence is when the droplets permanently fuse together into larger drops, completely breaking the film. And phase inversion is when an oil and water mixture completely flips inside out to become water and oil. Both of these mean the emulsion is permanently destroyed. Game over. And it's not just physical breakdowns we have to worry about. We also have to fight off microscopic invaders. You see, bacteria absolutely love snacking on the natural vegetable gums we use to stabilize these formulas. Because of this, chemists must carefully calculate preservative concentrations. They have to ensure the preservative doesn't just hide away in the oil layer, but actually partitions effectively into the water phase, because that's exactly where the bacteria thrive. On top of that, the preservative has to remain unionized so it can actively penetrate those bacterial membranes and do its job. Let's move to our final topic. Section 6, the HLB system. So, with all of these complex factors constantly working against them, how do formulation scientists choose the exact right surfactant armor for their specific oil and water battlefield? Well, they rely on something called the HLB scale, which stands for hydrophilic lipophilic balance. This scale helps them perfectly match polar and nonpolar properties. Following something called the Bancroft rule, the emulsifier will form the best emulsion if it dissolves most easily in the liquid that will become the continuous outside layer. So if you want water on the outside, you pick an emulsifier with a high, water-loving HLB number, somewhere between 8 and 16. But if you want a greasy ointment with oil on the outside, you go with a low, oil-loving number between 3 and 6. In real-world practice, they almost always blend them. For example, let's say a pharmacist needs to hit a highly specific target HLB of 12.1 for a liquid paraffin lotion. They aren't just going to find one magical chemical off the shelf that perfectly matches that number. Instead, they do the math to precisely blend two different agents. By mixing exactly 27% of a low HLB agent called span 80 with 73% of a high HLB agent called tween 80, they can create the perfect, custom-tailored mediator for that exact lotion. So where does the science go from here? Well, at the absolute cutting edge, scientists are creating these things called microemulsions. By pairing a standard emulsifier with a special co-surfactant, something like pentanol, they can drop the interfacial tension all the way down to near zero. This is a huge deal because it enables spontaneous emulsification. That means it mixes practically on its own without any harsh shaking required. The droplets are so unbelievably tiny, we're talking 10 to 200 nanometers, that the liquid actually looks crystal clear, and it can carry poorly soluble drugs incredibly deep into your skin. Let's leave you with this final thought. We've explored the incredible physics of surface area, the clever math behind Stokes' law, the weird magic of flocculation, and the chemical armor of the HLB system. Knowing what you know now about the epic, invisible war between physical chemistry and gravity, will you ever look at a simple bottle of cough syrup or hand cream the exact same way again? Thanks for joining us for this explainer, and as always, keep questioning the science of the everyday.